So till now we got an idea that what available energy is, how to calculate that, and how to calculate the loss of available energy when the heat is transferred from one place to the other. And we got to know that available energy is nothing but the maximum work that you can extract, right? And you use heat engine, reversible heat engine, to extract maximum work from an heat transfer. Now what I'm going to do is that I will be covering all the possible cases of heat transfer and how to calculate different things related to availability that can be asked to you in any of the exam, because the cases that I'm going to cover right now are going to be so much exhaustive, means so much elaborative, that they will cover all the cases that are possible for heat transfer, and this much elaborated approach to all the cases you will not find in any other source. Okay, so right now I have shown 3 cases, total 6 cases we will be covering. The rectangles shown in any of the diagram is obviously showing the thermal energy reservoir. Okay, the oval shapes like this and here is showing a finite body which has obviously finite mass and a finite specific heat, and this circle is showing the heat engine. So first case is that when heat is being transferred from one thermal energy reservoir to other thermal energy reservoir. Second case, when heat is transferred from a finite mass to thermal reservoir, and third case when it is between two finite masses. Okay, in all the 3 cases, if I want to calculate that what is the available energy or what is the availability of this heat transfer, then I have to use a heat engine, right? In reality, there is no heat engine. In reality, this is the case of just heat transfer, heat transfer, heat transfer. No actual heat engine is used there, but I want to know the availability. For that, I need to know what is the maximum work that we can extract. For that, I have used a reversible heat engine. Okay, in reality, it is just the case of heat transfer. So if I want to calculate the availability for it, then what I can say that availability or available energy for this case is same as loss of available energy. Do not get confused from the previous case. In the previous case, other than the 2 reservoir, we had third reservoir as well. I will come to that case in the same approach. I will cover those cases also. So just don't get confused from that. We just have 2 reservoirs here. So how much is the maximum work we could extract from that? That much is the loss, because in reality we are not extracting any work. It is just heat transfer. Heat is just flowing from one place to other without doing any work. So how much work it could have done, it has wasted now. Hence, for all the 3 cases, available energy is equal to loss of available energy. Okay, so question asks loss of available energy. It means it's just asking you the available energy itself when it's just heat transfer. Now in this case, if I want to calculate any of these, because both of them are same, then how can I calculate available energy? It is equal to W max, which is W reversible, right? To calculate W max, we take this as Q. Let's say this is T1, this is T2, and this is W, correct? To calculate W max, we use the approach of efficiency multiplied by Q. Let's call it Q only. It is Q minus W. Right? We write then efficiency as 1 minus T2 by T1, and we simplified it. Other than this approach, you can use one more approach which is going to be universal, which is going to be same for all. That is the approach of delta S universe is equal to 0. You just use this. You just remember this, because there are multiple cases possible. You will confuse that where to use which one. So just use this everywhere. Delta S of universe 0. What is in the universe? This much. For heat engine, there is no delta S. For this, delta S is going to be minus Q by T1. For this, delta S is going to be Q minus W divided by T2. And that should be equal to 0. Right? The heat that second reservoir is receiving is Q minus W. Now you simplify it. It is going to become Q minus W by T2 is equal to Q by T1. you bring this T2 here and you write it as W is equal to Q1 minus T2 by T1. It's the same as efficiency multiplied by Q. You might be thinking that when we are directly getting efficiency multiplied by Q, then why are we going through this much, means these two steps? You are absolutely right, but as I told you that finding efficiency is easy here because the temperatures are fixed. But in this case or in that case where both the temperatures are continuously changing, then finding efficiency is going to take the integration. You need to integrate that. That is going to be somewhat, not very lengthier, but somewhat difficult to understand at that point. So according to me, just use one thing and you will be able to apply this everywhere. So what is the problem in that? Just use delta S universe is equal to 0 for every case. So for this case, you have calculated W max, correct, which is equal to this. Now coming to this case, if you want to calculate AE or loss of AE, we have to use delta S of universe is equal to 0. And now is the time to recall. Recall that we covered a case in entropy when we wanted to find out the maximum work we can extract from heat transfer between a finite body and a thermal energy reservoir, right? You remember that? I told you two things in that. I told you that this expression of delta S universe greater than equal to 0, which seems very useless, but it's very important for numericals. And I applied the same concept to find out an expression. And I told you that first thing to keep in mind is that you have to use delta S universe greater than equal to 0. And second, the final expression, correct? So I am going to write the final expression first, then I will be telling you how we perform that. So using delta S universe is equal to 0, we got that W max is equal to MC. If this is, let's say, mass M, specific heat C, temperature T, and this is at, or let's keep it as T1, and this is at T0, the surrounding. So MC, earlier we used T here in place of T1, okay, so there is going to be T1 in place of T. T1 minus T0 ln T1 by T0, right? This was the expression that I told you to remember. And how did we reach at this expression? By using delta S universe is equal to 0 only. How? Delta S of universe means delta S of this plus delta S of this plus delta S of this. For this delta S is 0 because cyclic process. For this delta S is going to be delta S for body 1 is going to be MC ln final temperature. Ultimately it will cool down to T0 by T1. For this delta S is going to be, or let me add it here only, delta S1 plus delta S for this is going to be Q minus W divided by T0 because it's a reservoir. How much is Q? Q is equal to MC T1 minus T0. Q minus W. This much is the heat that it is receiving divided by T0. This is delta S universe, which should be equal to 0. Now you multiply T0. So 0 will remain 0. Here you will get T0. Here this T0 will go due to multiplication of T0. And this is minus W. You bring minus W on this side. You will get W. You take MC common. So if MC comes common, you will be having T0 here. And MC will be removing from here. And if you simplify that, it is T1 minus T0, this one. It is T0 by T1. You reverse that. You write it as T1 by T0. So minus 1 side will come. It will come here due to property of log, which is minus T0 ln T1 by T0. Minus T0 ln T1 by T0. Same expression we are getting. What did we use? Delta S universe is equal to 0. Correct? So using this approach, this was the expression that we got earlier. I just did that derivation quickly because we have already done that. Coming to that case, if I want to calculate, and yes, this is same as this one. This W max is nothing but AE only, right? You see how it is related with the entropy, right? Available energy is so much related that the same expression that we derived in delta S is going to be used as available energy because Available energy is nothing but maximum work extracted from a reversible heat engine. Whenever reversible word came, means delta S universe is equal to 0. This is the concept of entropy. So this is how the available energy and entropy are closely linked together. Similarly, in this case, you recall that I told you that whenever we are going to transfer heat between two finite masses, the range of work will vary from average temperature to geometric temperature, from T1 by T2, T1 plus T2 divided by 2, which is the mean temperature, arithmetic temperature, to the geometric temperature, root T1, T2. Correct? When you will be getting mean temperature? When there is just heat transfer going on. So ultimately they will come down to a final temperature which is going to be T1 plus T2 by 2. But when you are extracting work from that and you actually want to see that how much work we can extract from that, in that case final temperature is going to be root T1 T2, which is the geometric mean. And in that case I told you that we derived actually that the final work which you calculated from delta S universe is equal to 0 only, which was W max, was equal to C root T1 minus root T2 whole square. If you do not remember this, go back to the previous video, watch it again. And this expression is same as the available energy, right? So in all the three cases, available energy is equal to loss of available energy, and to find that expression you just need to apply delta S universe is equal to 0. In some of the places you will also find another approach that is not actually another approach, that's a modification of this one only, that you can write W max as Q minus Q T2 by T1, right? And this is, let's say, T naught, heat transfer between T1 and T naught. So this T2 is going to be T naught. So T naught multiplied by Q by T1. And Q by T1, this Q by T1 is actually the change in entropy of this reservoir, but absolute value, because actual change for this is going to be minus Q by T1, but the absolute value is going to be Q by T1 only. So this they write as Q minus T naught multiplied by delta S of source. This is W max, which is ultimately going to be AE, right? So this is also an expression which is used sometimes, but I do not recommend learning this one, although it can become somewhat easy for you to solve this question or this question also, because here you see what is this, MC T1 minus T naught. What is this? Total heat that is being transferred, which is Q only, minus T naught multiplied by delta S mod of source. For source, how much is going to be delta T? MC ln T2 by T1. MC ln T2 by T1, but even if you multiply that, even if you change this ratio here, the sign here will change, but here it is the absolute value only, right? Here whatever value you are going to use for delta S does not matter. Ultimately whatever value will come out will be positive only, correct? So here T1 by T naught is positive already because T1 is large, hence this value and this value will match because this is always going to be positive, and ln T1 by T naught is obviously positive because numerator is larger than denominator, right? So in this way you can also connect this expression with this. So you may think that this one is easier to learn, let's learn this, but I do not recommend learning this, because actually what we are doing is applying this concept directly for this question by generalizing the equation, correct? Conceptually it's not something which is going to help you a lot, because there are going to be certain questions where using delta S universe is equal to 0 is going to help you. I'm not going to talk about those questions right now, we will be covering them, but using this expression will only help you in these limited cases, but not everywhere. Now in these two cases, and especially this case, there is one more type of problem that is probable to be asked. What they are going to do is that they will not allow this body to be cooled up to T naught. They will stop it at some temperature, let's say at T2. So the cooling will only go from T1 to T2. So if surrounding or T naught is at, let's say, 300 Kelvin and this body is at 800 Kelvin, so basically it is supposed to cool up to 300, right? But they will only allow it, let's say, to cool up to 500, and then they will ask you what is the maximum work that you can extract, or what is the availability of heat being transferred when this system cooled from T1 to T2 or 800 Kelvin to 500 Kelvin. So how can you do that? Same concept, delta S universe is equal to 0. For that, delta S of universe is going to be delta S of this body, which is going to be MC ln T2 by T1, correct? This is T2. Plus, how much is the change in entropy for this? Q minus W, and Q is equal to MC T1 minus T2 minus W divided by T0 is equal to, this should be equal to 0 because delta S universe should be equal to 0 for reversible. Now what you can do is, again you can divide this MC T1 minus T2 by T0 with W, or let's say multiply T0 with this first. So after multiplying T0, we will get T0 MC ln T2 by T1 plus MC T1 minus T2 minus W is equal to 0. Correct? Now what you can do is, you can take minus W on this side, so it will become W. So W is equal to, or let me write W here, W is equal to this expression, and again you just have to follow the same process. Take MC common, you will get T1 minus T2 and you reverse it, so it will become minus T0 ln T1 by T2. This is available energy, maximum work, because delta S is 0. Now compare this expression with this one. This is for the case when it is cooled up to T0. This is for the case when it is just stopped at T2 before reaching T0. What is the difference? This T0 is replaced by T2, this T0 is replaced by T2. This is the T0 which will remain intact. This is the only difference in those two equations. So either you can directly learn this equation that other than this T0, every T0 is to be changed to T2, or you can just do this derivation. It's just a 1 or 2 step process, correct? So this is another type of question that can be asked to you from this case. Same case can be applied here also, where very rarely it can be asked, but it may be possible that they will give that this T1 will be cooled up to T3 and this will be cooled up to T4 only. So how much should be the maximum work? Same concept you have to apply. Delta S for this plus delta S for this plus 0 means delta S for heat engine should be equal to 0. You go on with the derivation, you will get the answer. However, it is not very likely to be asked, and to be very honest, GATE has not even reached to ask this level. At this level also it has not reached, right? So there are very less chances that they will reach even there. But even if they have not reached, but we are prepared for it, and this concept which I told you, that I have covered all the types of problem that can be asked from these 3 cases, this will help you not only in GATE but in any other exam. So we have covered 3 cases. Now we are going on to cover next 3 cases. The difference in next 3 cases is that here we were not having any third reservoir. The heat was being transferred between 2 systems only. But in the next 3 cases, we will be having a additional reservoir as well, a third reservoir as well, and then I will tell you that what are the types of questions that can be asked from those cases. So as I told you, in this case, we are not only having the 2 reservoirs between which heat transfer is going on. In addition, we also have a third reservoir present. Now, heat may not be directly transferred to that reservoir, but that is present in the question which is given to us, or in the problem statement which is given to us. Consider this case to be the case as if you have a very large room, okay, one very large room which is connected to another very large room, and there is some heat transfer going on between them, okay, and these 2 rooms are present obviously in the environment, in the atmosphere around them. Since both the rooms are very large and the ambience, the atmosphere around is also very large, we can consider all of them to be thermal reservoirs. And since heat transfer is going on between one room to the other room, so only those 2 rooms are the reservoirs between which heat transfer is going on without any transfer of heat to the atmosphere around them. So this is what you can consider that I have shown here. This is one room, this is other room. Heat transfer is going on between them and there is atmosphere also present. higher temperature T1, lower temperature T2, ambient temperature T0. There is no any actual heat engine employed, as I have repeated so many times. This is just a heat transfer, but we want to calculate, if we want to calculate the maximum work that we can extract from that heat transfer, then we are going to use a heat engine. But in this case, in the case that I am telling you now, heat engine is of no use. Let me tell you why. Because the type of questions that you will get in all of these cases is the one where they will ask about loss of available energy. In all of them, loss of available energy. Because whenever heat moves from higher temperature to lower temperature, its ability to perform work has decreased, right? We have already covered that higher will be the temperature of source, more will be the ability of heat to do work. The heat which is present here, which is coming down, has more potential of doing work. But if you extract the same heat Q from T2, then that heat will be having a less potential of work, correct? How much potential of work does this heat Q has at T1? How do you calculate that? What is availability? The maximum work that you can extract from the heat, right? I am repeating it so many times, but what to do? So it is the maximum work that you can extract. Now, when you can extract maximum work? When the temperature difference will be maximum, right? When temperature difference is 0, there is no heat flowing, no work can be extracted. More will be the temperature difference, delta T, more will be the Q. More will be the Q, more work you can extract. So if I want to calculate that how much work can I extract from the heat which I get from T1, then you would not transfer it to T2. You will transfer it to such a reservoir which is even less in temperature than T2, and let's say T0 is the least of all. So we will use this heat engine not between T1 and T2, but between T1 and T0, and we will see how much work, maximum work we can extract if a heat engine is employed between T1 and T0 or between one room and the atmosphere. That will tell the work potential of that heat. Similarly, if you want to calculate how much is the work potential for T2, you will use a heat engine between T2 and T0 and not this heat engine. This heat engine is, as I told you, of no relevance for this case. So we will use heat engine between T2 and T0 then. And then we will compare that which one is higher, which one is lower. Clearly this one is higher because we have already done this. If you recall, we have done exactly this analysis few videos back. So this is the same analysis. So if they ask about loss of available energy, so that is equal to available energy at 1. How much is the available energy present if the heat is coming from here, minus how much is the available energy if the heat is coming from second body. So from first, you have to use the heat engine between T and T0, right? So just it's the same case of having two reservoirs. We did 3 cases earlier for all 3 of them, and that was the case of just 2 reservoirs. So same case, same results are to be applied firstly for T1 and T0, then for T2 and T0. So for T1 and T0, AE1 is equal to Q1 minus T0 by T1. Similarly, AE2, available energy 2, that can be extracted from 2, is Q1 minus T0 by T2. This is the loss in available energy. Similarly here, we have T0 present. So how much is going to be the loss of available energy? That is equal to available energy present at 1, this is 1, let's say, and minus available energy present at 2. How much is the available energy of 1 means how much work you can extract when you supply heat to the minimum temperature present. So this is the case that we did earlier in the first three cases. So how you are going to do that? You just have to put the value MC T1 minus T0, T0 ln T1 by T0. This is the maximum work that you can extract when you allow the heat to transfer from one finite body to a thermal reservoir completely, correct? And thermal reservoir in this case, I am repeating, is not going to be T2, is going to be the minimum temperature available. That thermal reservoir which is of minimum temperature, that we are going to use to calculate maximum work, because that will be having maximum temperature difference. Okay, minus AE2, how much work you can extract if this heat is released from T2 to T0. Okay, so it's a reservoir again, from one reservoir to other, the same case as this one. So this is the value of work that you can extract from that, T0 by T2, correct? To know the loss or decrease in available energy for the third case, let's solve an example rather than knowing the theory. Now let's solve this question. It says that calculate the decrease in available energy when 25 kg of water at 95 degrees Celsius mix with 35 kg of water at 35 degrees Celsius. Okay, you have to take the pressure to be constant, means in this mixing the pressure is constant, and temperature of the surrounding is 15 degrees Celsius. The value of specific heat at constant pressure is also given to you. Okay, try to solve it. So for such cases, when we have two different masses and an atmosphere or a reservoir present, we need to calculate the loss of available energy. For such cases, you have to find out, firstly you have to understand that what exactly is happening here. Here heat transfer is affecting both of them. Like in the first case that I told you, when both of them were reservoirs, in that case heat transfer was not changing their temperature. But when both of them are masses, then heat transfer is affecting both of them. At the final state, they both will reach at the same temperature. So if I ask you that how much is the loss in available energy, then you are not going to compare the first mass with the second mass and the difference of them is going to be available energy. That's not how we do it. Loss of available energy is that how much is the available energy that we have before heat transfer and how much is the available energy we have after heat transfer, because after heat transfer their temperature difference will decrease and they will finally attain a final temperature. So we will first calculate the total available energy of 1 plus 2, that is the total available energy that we have initially, minus how much is the available energy we will be having when both of them will reach the same temperature. That is going to tell that due to that heat transfer how much available energy we have lost, correct? So in that case, firstly we have to calculate the available energy for 25 kg of water. We have two different masses, 25 kg water and 35 kg water. So we will individually calculate their available energy by considering the lowest temperature given to us, which is 15 degrees Celsius here as the atmosphere, as the T0. So to calculate available energy of mass, we know that we use this expression. The question has mentioned the specific heat to be a constant pressure specific heat. So we will be using Cp. Similarly, for other expression also we will be using Cp. So in this expression, just put the values, but keep this thing in mind that temperature you have to convert into Kelvin, especially for the ratio. Because for difference, it does not matter whether the temperature is in Celsius or Kelvin. You have to add 273 to both of them. Sign is negative. Ultimately, they will get cancelled. So it does not matter whether you add 273 or not. But in the ratio, it matters. Correct? Because ratio of A by B is not equal to 273 plus 8 divided by 273 plus B. Correct? So let's convert them in Kelvin only. The mass is known to us 25, Cp is known to us. After putting the values, you will get 987.49 kilojoule as the available energy for 25 kg. Similarly, using the same expression for 35 kg, mass is going to be 35 here and temperature T2 is going to be 308 Kelvin after converting 35 degrees Celsius into Kelvin. And you put the value, you solve, you will get 97.59 kilojoule as the available energy of 35 kg. So the total available energy that we have is the sum of these two, which will come out to be 1085.08 kilojoule. This is before mixing. Their individual available energy added together. But after mixing, we will reach a final temperature and let's call that temperature capital T. And how to calculate that? The heat loss is equal to heat gain. Correct. So that's what we have done here. MC delta T. Delta T I have already told you you can keep it in Kelvin, but where there is temperature difference, it does not matter whether it's Kelvin or Celsius. So mc delta T is equal to mc delta T for the other one. From this you will get the temperature as 60 degrees Celsius, which in Kelvin will be 333 Kelvin. Now you need to calculate the available energy for mass of 60 kg at 333 Kelvin when ambient temperature is known. How mass is 60 kg? Because now both of them are mixed. So total mass is 35 plus 25. So put that again into the same expression and solve it. You will get this much is the available energy with the final mixture. So how much has the available energy decreased? Just have to take the difference of both of them. You will get 281.81 kilojoule as the answer. Okay. Now suppose we have a Carnot engine, a reversible engine which is used between temperature T and T0. It is receiving heat, it is doing some work, and then it is rejecting heat. Correct? If I want to plot the cycle which is going on inside this heat engine on a TS diagram, then how can I do that? As I told you, suppose that it is a Carnot cycle which is running inside this heat engine, right? So Carnot cycle will be having 4 different processes. First one is going to be reversible isothermal, then it is going to be reversible adiabatic, then again reversible isothermal, then again reversible adiabatic. In this way the cycle will get completed. Correct? Okay. What is available energy? For this system, what is going to be the available energy? The work that this Carnot cycle is producing, because that's going to be reversible work or the maximum work. In TS diagram, what is the parameter which is showing this work which is being produced? We have a cycle, whether it is TS or whether it is PV, we know that the net heat interaction and the net work interaction are same, and they are shown by the area which is enclosed by the curve, by the closed curve. Correct? Hence in TS diagram, this area is showing the available energy, this area enclosed by this rectangle. Correct? Let me name also these processes 1, 2, 3 and 4. Okay. In moving from 1 to 2, it is absorbing heat, which is just Q here, or let's call it Q1. We will also write it Q1, and let's say this is Q2, which is equal to Q1 minus W. So from 1 to 2 it is absorbing heat, let's call that Q1, and from 3 to 4 it is rejecting heat, let's call that Q2. Correct? If I talk about the area on TS diagram, then the heat Q1 will be represented by this area, this whole area. Correct? Because any line on TS diagram, the area below that line or below that curve tells the heat. So if I want to know how much is the heat absorbed from 1 to 2, that is going to be the area below that line or below that curve. So this full area is the Q1. And in moving from 3 to 4, this area is Q2. For this cycle, Q1 is the heat that it absorbs, Q2 is the heat that it rejects. Hence, difference of both of them is going to be the work, right? Which is available energy. This also tells us that the heat being rejected, Q2, this heat is nothing but this area, right? And what do we call Q2 in this cycle? This is called as availability or the available energy, and this Q2 is called as unavailable energy, the energy which is not available for work, which could not be converted to work. Hence, this area here is unavailable energy. And this is not true only for this Carnot cycle. Whatever be the type of cycle, any general cycle you draw on TS diagram, be it in circular shape or any random shape, the area enclosed by that is going to be the available energy, and this area below that is going to be the unavailable energy. Okay, so this is going to help you in numerical problems that can be asked directly from the graph. Question can give you directly the graph and such things can be asked to you. So knowing these details will help you there. Now this heat engine and the process going on are plotted there. Consider one more heat engine which is similar to this one and that is operating between temperature limit T dash and T naught. And the temperature limits are such that T dash is less than T from this. So temperature gradient, total temperature gradient or total temperature range available has decreased now. This is the heat engine which is working there. Let's call it W max, the work which it is producing. Now whether this W max is same as that one, we don't know. So let's put a dash there. Now what we have to take is that whatever is the heat that we are supplying, same heat is being supplied here as well. It means Q1 is the heat which is being supplied to the heat engine in both the cases. So heat engine is receiving the same amount of heat. But will it produce the same amount of work? How can we know that? We already know that the work that any heat engine produces not only depend upon the heat which is supplied to it, but it also depends upon whether it is reversible or not and whether the temperature range available to it has increased or decreased. Now both of the engines are identical, both of them are Carnot engine or any reversible engine. Both of them are having same heat, but the temperature range available to this heat engine is less. Hence, how much work it can do automatically gets reduced. Correct? So means these are things that we already know. But let's see that on the graph. So we have to take Q1 as same. What is Q1? Any general heat, not necessarily Q1. What is Q? Q is T delta S. Correct? For this case, for this cycle which is representing this, let's say this is T, the higher temperature, this is T naught, the lower temperature, and the heat being supplied, which is Q1, is equal to T multiplied by delta S. This is the delta S. Correct? Q1 is equal to, for this case I am talking about, T multiplied by delta S. So this is Q1. In this case, we have kept the Q1 as same. The heat being supplied is same. But temperature has reduced. So let's say T dash is somewhere here. So the cycle now is going to be like this. How? Since Q is same, so T dash multiplied by delta S dash should again be equal to Q1, where delta S dash is the new change in entropy in the cycle. Since T reduced, so delta S will increase because multiplication of T and delta S is constant because same heat is being supplied to both of them. So this curve is showing the earlier case of this reservoir and this curve is showing this case. Correct? I'm sure you are able to see. If you are not, then I'm just drawing it again like this, so you can clearly see that this is the earlier curve. Okay, and this is the current curve. Now let's compare both of them. This area below shows the unavailable energy. Correct? So the area below the initial curve, below the initial cycle is the unavailable energy for this case. But after drawing the second curve, you can clearly see that unavailable energy has increased. And why it is increased? Because Q is same, T has to reduce, because in this case T is less. But if Q is same and T has to reduce, then delta S has to increase. So this will automatically increase. So this area below will also increase. So the area below the curve or the unavailable energy has increased by the dotted region, by this region. Correct? Questions may be framed from that as well. How much is the increase in our unavailable energy? Using the graph only. By using these diagrams, it's very easy to tell. You can just calculate and take the difference. But graphically also they may ask you. So this much dotted region is the increase in available energy. Now consider that both of them are, getting the same heat, but unavailable energy has increased. Suppose this was 10, this is also 10. It was producing a work of, let's say, 7, and unavailable energy was 3 earlier. But now you can clearly see that unavailable energy has increased. So this has become, let's say, from 3 to increase to 4. So it will automatically become 6. So available energy or the area enclosed by this curve will automatically decrease. Correct? So these things visually, it's not possible to tell you, right? You can say that this area looks larger than this one, but if both of them look similar, then how can you tell that? If T dash is only little bit less than T dash, it's like this, then how can you tell, right? So these differences you can only tell conceptually, that unavailable energy decrease, Q is same, hence the area of the curve will decrease. Okay, so these types of question can also be framed from that. So this is something which we already know of, correct? By seeing that unavailable energy increased, we concluded that work, the available energy, this one must decrease, correct? Because Q is same. But that we have already concluded from the theory, that the temperature range decides that how much work is to be produced. If temperature range decreases, work decreases. We had already concluded that earlier, correct? So the graph is also supplementing what we already know. We also know that higher will be the temperature from which heat is being rejected, more will be the available energy. That is also being verified from it. This is the case when the temperature at which we are getting heat is more. In this case, we are getting the same heat, T delta S is same, but it is at a lesser temperature. And we have concluded that the available energy for this case will be more, right? This area is more because unavailable energy is less. So graph is also concluding that higher will be the temperature from which we are getting the heat, more will be its available energy or availability.